So let's talk about section 3.6, curve sketching. This is basically using intercepts, like x and y intercepts, your relative max, relative min, which are your relative extrema, and your concavity to sketch a curve, to graph it, to see a really good approximation of what it looks like without a graphing calculator. Now yes, your graphing calculator will do it for you, but to understand why these graphs are shaped the way that they are, you need the calculus. You need to really understand why they are the way that they are. Shall we do an example? Yeah. I'll tell you what I'll do. I'll give you an example, and I'll give you the steps as we go through that. Would that help you? So here's your example. Here's your example. And I'll tell you how to do this problem verbatim, just exactly like you should, all right? With every single step. Step number one, when you're graphing any curve, is, well, you want to find out as many intercepts as you can. X-intercepts and Y-intercepts. That's always a good thing to do, right? Because in most cases, that gives you at least an approximation of what you're talking about, where you're crossing the Y-axis, where you're crossing the X-axis. So step number one, every time, you're going to find the intercepts. By the way, how do you find x-intercepts? How do you find x-intercepts? Say it?
Y equals 0.
Y equals 0. So set the equation equal to 0. That's how you find x-intercepts. You set it equal to 0, you solve for x. That's going to give you any roots. That's what a root was, right? When you set the function equal to 0 and you solve for x, you're finding out where it's crossing the x-axis. That's the whole exact idea. Should make sense, right? Because if you set y equal to 0, that means you're going to find out everywhere you cross that x-axis. You believe me? Now, the y-intercept is quite a bit easier. By the way, you only do this step if it's easy. Easy means it's quadratic or lower, or it's already factored for you. Okay, so cubics, don't spend your time factoring them. If I give that to you on a test, I'll just give you the x-intercepts. I'll say, here are your 3 x-intercepts. You follow me on that? So if it's easy, do that. Easy means, so I know this is recorded so you don't cheat me, easy means quadratic, linear, or if it's already factored for you, that's easy. Everything else, cubic or higher, is hard. Unless you can just see a root right off the bat, that would be considered easy. Believe me? With me? Okay. If it's easy. For y-intercepts, how do you find y-intercept? Easy, really easy to do.
X equal to 0.
Set x, plug in 0. You plug in 0 for x, and it'll give you a y-intercept. That's the easy one. That's nice. You all need to find that for every single one of these, if it exists. Let's try it. Let's try it. So this will be step number 1. I'll try to write out every step for you. Step number 1. Solving for x-intercept. How do you solve for the x-intercept? Well, this is just basic algebra. You're going to take your function, you're going to set it equal to 0, and you're going to solve for x. So we will have x plus 2, x minus 1 squared equal to 0. Can you find your x-intercepts from right there? That's great. That's great, because it's already factored for you. Can you tell me what's one of your x-intercepts? You'd have x plus 2 equals 0. X minus 1 equals 0 because of zero product property. So x equals negative 2, very good, and x equals 1. You have 2 x-intercepts. Raise your hand if you feel okay with that. If this hadn't been factored for you, you just skip it. I'd give them to you, okay? Part 2 of step number 1 is find your y-intercept. Y-intercept says you need to plug in 0 for x and see what you have. So I'm going to take 0 plus 2 times 0 minus 1 squared. Don't forget to square it before you multiply. What is 0 minus 1? Negative 1 squared times is? 2. You get 2. The y-intercept is 2. Do you feel okay for this so far? All right, step number 2. Step number 2 applies only to rational functions. It does not apply to polynomials because polynomials do not have this. I'm going to put step number 2 and a little asterisk. The asterisk means for rational functions only. For rational functions, a lot of times with rational functions, you're going to get some asymptotes, right? You're going to get some holes. So for rational polynomials, they don't have those. It's continuous everywhere. You don't have asymptotes, you don't have holes. So this is why it's only for rational functions. You're going to find all the asymptotes, vertical and horizontal, and any holes. Do you remember when vertical asymptotes exist? Denominator equals what?
0.
And you can't. When do holes exist? Okay, so denominator equals 0 gives you asymptotes or holes. If you can cross it out, it's a hole. If you can't cross it out, it's asymptote. Vertical asymptote, denominator equals 0, non-removable. Hole, denominator equals 0, removable. How do you find horizontal asymptotes? Good thing we covered that stuff. Horizontal asymptotes occur. That's what the whole last section was about. It said, can you find the asymptotes as we go to the right, as we go to the left? That's what we were finding. We're finding horizontal asymptotes at zeros or at ones. That's what that did. And so what we're going to do here for horizontal asymptotes, you take the limit. Some more? You take the limit as we go x approaches infinity or x approaches negative infinity. You have to do both of them because you know the limit could change. Remember that 1/3, right? It could change, so you got to be careful on that. Take the limit. So, do we need to do step number 2 for that problem? Is it rational? So if it doesn't have a denominator, we're not going to be able to do that. If it had a fraction, you had denominator with a variable down there, then of course we would be doing that. But right here we don't. So now we're going to go on to step number 3. Step number 3 is you finally get to do some calculus. You're going to do the first derivative test. You remember the first derivative test? You had a whole homework section on that, right? First derivative test, you said equal to 0. It will give you 2 things. Critical numbers and increasing, decreasing. And that's what you care about, right? You care about where are my maxes, my mins, how am I going up, how am I going down. That's what you care about. First derivative test. Why? Because it's going to give you critical numbers and increasing, decreasing. Or areas where the graph will increase or decrease. Hey, let's try that now. We'll get, you know what, maybe I'll give you all the steps and then we'll go through it. Step number 4, sorry, I'm kind of backwards. 1, 2, 3, just pretend we're reading a book backwards or something. Step number 4, after you do the first derivative test, what do you think you're going to do next? Geniuses. The second derivative test. What does the second derivative test give you? Yep, the reason why you do it, just like Scott said, you're going to do for concavity and for inflection points. Step number 5, remember the table I had you make that has the first derivative on the top, second derivative on the bottom. It tells you increasing, decreasing, increasing, all that stuff, and it tells you concavity. So basically, it gives you a picture of your graph right there. That's what you make. So make the table.
These problems are very
You know, they're very long problems. Especially, oh my gosh, especially with rational, they take a long time, a very long time. They're not easy. Well, actually, they're not hard. They're very time consuming. So they're going to take a long time. Not going to lie. Number 6. At this point, you're going to have everything you need, all right? You're going to have your intercepts. That's huge. You're going to have any asymptotes. You'll put those on your graph. You're going to have any holes. You put those on your graph. You'll have your critical numbers and your inflection points. What you won't have is the actual points, right? You'll have critical numbers, plug them in, find all possible points, relative maxes, relative mins, and inflection. Find your points from the original function. The last, if you get the points, you get all the areas of increase and decrease in concavity, graph it. Okay, we're going to get at least the first 2 tests done on this thing. We already have the intercepts. We got x and y. We don't need to do step number 2 because they're not rational. We're going to do the first derivative test. Now, don't fool yourself here. Yes, that looks pretty nasty. That you say, oh my gosh, that's a product rule with a chain rule or a general power rule in it. That could get pretty hairy and then have to set equal to 0. Or maybe be a little bit smarter about that. Probably easier to distribute that, right? Maybe distribute some of those easier ones first. That way you don't have to do all those rules. Now, if it was to the 6th power or something, firstly, that'd be insane. But secondly, you wouldn't want to do that. So just go ahead and maybe distribute that. So why don't you try that right now? Hopefully you got that. Did you get that? Okay, keep working. Step number 1, we got. Step number 2, we don't need it. Step number 3. Firstly, were you able to get that? How'd you have your word? You able to get that? Yeah?
Yeah.
Take the first derivative. Do the first derivative test. Go for it. By the way, that a whole lot easier to take the derivative of than that, right? Try that on some of those graphing ones. Right? It's usually going to be something doable for you, at least doable. So try some of that. So take the first derivative. Let's do that together. Everybody, what is the first derivative when I do that? What was that? What do I do for a first derivative test? If I set that equal to 0, I'm going to get x equals, well, I'll show the work on that if you really want me to. This will be 3x squared equals 3, x squared equals 1, x equals plus or minus the square root of 1. X equals 1, and negative 1. You okay with that so far? Okay. Hey, that's the first derivative test. That's not too bad. Let's do step number 4. Step number 4 is, can you do the second derivative test? Second derivative test says, well, take the second derivative. Go ahead and do that now. Take the second derivative. How much is the second derivative?
6x.
Oh, that's beautiful. I love that. What do you do with that 6x? When you solve for 0, what are you finding here?
Inflection point.
You're trying to find possible inflection points. So when you divide by 6, x equals 0. These right here are your critical numbers. This right here is a possible inflection point. Let's recap for just a second before I start making the table for you, and then we'll do the table next time. How many people feel okay on finding the x and the y-intercept? Feel all right with that? Good, that's our basic algebra. Do you feel okay with our first derivative test and our second derivative test? Raise your hand if you feel all right with that. Now, step number 5, this is where all your work happens, okay? All your work happens right here in step 5. You're going to have what you got from your first derivative, you're going to have what you got from your second derivative, and you're going to put all of it on something that looks almost like a graph. It's a number line. What were our critical numbers that we needed? What were our critical
Plus or
numbers?
minus 1.
So, negative 1, positive 1, 0 goes on the bottom. Why does 0 go on the bottom?
Second derivative.
Okay, so critical numbers went on the top. That was our first derivative. That's what we got, right? Possible inflection points, that's from our second derivative. That goes on the bottom of our table. It has to be in order, negative 1, 0, 1. Do you feel okay with that so far? What do you do now?
Start testing numbers on any one section.
So every single interval here, you follow? What number are you going to check here? And where are you going to check it? In the first derivative. What are you going to check here? What was it? Negative 1 would work, right? Doesn't matter. Negative 1, you're going to check it in the
Second derivative.
Okay. Why don't you go ahead and do that. Fill that table out for next time, because that's where I'm going to start next time. If you want to hang out for a second, I'll do it right now, okay? For this one, if I plug in f prime of negative 2, if I plug in f prime of 0, I can do that, and f prime of 1. I'm doing my first derivative. I'm going to get positive, I'm going to get negative, and I'm going to get positive. That means increasing, decreasing, increasing. You follow me on that? Yes or no?
Yeah.
Okay, second derivative. I'd try f double prime of negative 1. I'd try f double prime of positive 1. Remember, it's just this interval. It doesn't mean you can't plug those in for your second derivative. That's okay. Negative 1 gives you negative, concave down. Positive 1 gives you 6. That's positive. Concave up. Show of hands, some people feel okay with their concave down, concave up. That right there is a picture of our graph. We're done with step 5. This basically tells you up, down, up. We just have to find some points, and we'll graph that next time. Let's finish that problem. We're dealing with basically just a polynomial. We know that we can take a first derivative pretty easily if we distribute. We've already done that. We found first derivative test, second derivative test. We have our intervals of increasing, decreasing, intervals of concavity up and down. We also have our relative, which one is this, max or min? Relative max, relative, and good, inflection point. What we don't have is actual points, right? We need the points now. So the steps that we haven't done. After you've done your first and second derivative test, you've made me the table. What I want to see is your points. Now I know the x-intercepts automatically give us some points. Basically, 1, 0, negative 2, 0, those are my x-intercepts. My y-intercept will give me another one, 0, 2. So x-intercept, y-intercept. But then all of my critical numbers, my critical points, like my relative max and min, that's more points. My inflection point, that's another point. So you need to also give me, are you okay on the 1, 0, and the negative 2, 0? It's my x-intercepts. My y-intercept is at 0, 2. That's what we got those from. We did that last time, right? If you don't remember that, look back at your notes or look at that video. We did that last time. Now, those were x-intercepts, y-intercepts. We also have relative max. We have relative min. And we're going to have an inflection point. Just one in this case. Can you please tell me what's the x-coordinate for my relative max? The x-coordinate for my relative max. Negative 1 would be the x-coordinate for my relative max. You follow? How'd you get the 0?
Plugged it into the original function.
Good. The original one is what gives you points. So to find our points out, you take the negative 1, plug it back up into here, or this one would probably be a little bit easier, and that will give you out the y value. You follow me? That gives you your points. So this is going to be negative 1, let's see, negative 1 plus 3, 2. 2.
Is that?
I think so. I don't know. You tell me.
Because if you plug it into this 4. That's 4.
Okay. Ish happens, right? It's all good. What's a little point between friends, huh? A moot point. Right. Okay, negative 1 plus 3 plus 2, 4. Find your relative min. What's the x value for your relative min, please? What is that? So I'm going to put a 1 here. How do I find the y value? Plug it in. That one's going to be, that one's 0. Inflection point. Can you please tell me my x-coordinate for my inflection point? 0, 0, comma. That's an interesting point, isn't it? Not only is it the y-intercept, it's also the inflection point. So we have that point twice, not a big deal. You feel okay with the points? Here's how to label them on your graph. What you're going to do is just work your way down, just like we did with the process. Start with your x-intercepts. 1, 0, put a point. Negative 2, 0, put a point. Those are my x-intercepts. My y-intercept is 0, 2, put a point. Relative max happens at negative 1, 4. Put a point. Relative min happens at 1, 0. Put a point. That's already there. Now, here's how I like to label these points. Are you okay on, firstly, the 4 points that we get? I mean, we have 1, 2, 3, 4. We have 6 of them listed, but we have 2 pairs of points. Here's also what I like to do. When you have the inflection point, you need to label it inflection point. That way you see the change in concavity. So which one of these is inflection point? Well, it was the 0, 2, 1. So I'm going to label that inflection point, just IP, just so you know it's IP. For your relative extrema, your relative max and relative min, what I like to do, I like to draw a little dotted line. So for my relative max, which is at negative 1, 4, I like to do that. That says I can't go above that. For this one, this 1, 0, that I know that was a relative min, right? I'm going to do this. I can't go below that. I know that my graph is going to bounce off of those dashed lines. Do you follow me on that? That's what's going to happen here. It's going to, well, following our graph, go up, bounce off, hit an inflection point, bounce off, and then keep going forever. Does that make sense to you? So label those things with something like that. Do the inflection point, change the concavity. Do your relative max, relative min, do little dash lines. That way you know you're not going to go past that. You're going to be changing at those values. So let's see if we can graph our graph. If we follow this table and associate them with these points, we should have a pretty good looking graph. It says you're going to start out, you're going to be increasing. Which way is increasing? This way or this way? This way. So we're increasing. How are we increasing? Concave down. So increasing, concave down. Increasing, this is concave up, this is concave down. You follow? We're increasing, concave down. It says increasing, concave down. We're going to go through that point. So increasing, concave down. It's going to be hard to draw that way. tried to do it. Increasing concave down. Are you following me on this? I'm going to hit that, what it says, a relative max. Increasing concave down, relative max. Then I start decreasing. How am I decreasing? Look at the board here real quick. How am I decreasing for this interval? It says you're decreasing, but you're doing it concave down. You follow me? So for this little interval right there, it says x equals 0, right? It says from negative infinity to negative 1 on the x-axis, you're increasing concave down. From negative 1 to 0, you're decreasing concave down. That's this way. Decreasing concave down. You still okay with that? Yes, no. After 0, it says I'm still decreasing, but now I'm concave up. That's like this. Decreasing concave up. So that was my switch in concavity. I'm still decreasing from 0 to 1. From 0 to 1, I'm still decreasing, but I'm concave up. As best you can. After x equals 1, that's why I made the point earlier in the class that you have to follow the x-axis, right? You got to be on that. So you go, okay, after x equals 1, I'm increasing again and I'm concave up. Increasing concave up looks like that. That probably should be a little bit more narrow. But that's the idea. Can you get this graph from this picture of the graph? How many feel okay with that? So follow along the x-axis, start from the left, work your way right, increasing concave down until x equals negative 1. Right there, we have the point for that. For that little interval, decreasing concave down. Right there. For this next interval, decreasing concave up. Right there. Last interval, 1 from x equals 1 on, increasing concave up, and we have our picture. Now, of course, it's just an x cubed, so we kind of have a picture of that anyway. But the double root's interesting, right? We were able to find that. We were able to find all these points. That's a pretty accurate graph. Fairly accurate. How many feel just fine with it? All right. Now, I'm going to erase this because it's going to take us a long time. A lot of board space to do these problems. We're going to graph some rational equations. You ready for rational? Rational are harder, first because the derivatives are harder, and second because you have asymptotes. That's what makes them harder. So I'm going to try to get through 2 today. We have about 30 minutes or so, 35 minutes right now. So they take a long time. We're going to try to get through 2. Oh yeah, were there any questions on that? Now, the question is, do I do that on purpose? You'll never know. I'm not going to rewrite the steps because I gave them to you last time. They're on the video if you need to check those out again. The steps were 1 through 7. Number 1, x and y intercept. Number 2, asymptotes if it's rational. That's why we didn't have a number 2 up here. 3, first derivative test. 4, second derivative test. 5 is make the table up. 6 is make the points. And 7 is graph it. So we're going to follow the same 7-step process the whole way through. By the way, we are going to be dealing with some roots on this, so if you take your calculator out, I'm going to need some help calculator work from you on this. Okay, so x squared minus 1 over x cubed. Step number 1. Hopefully the algebra type stuff, you find your x and your y intercept. So we're going to do every step together here. X-intercept would happen where you set your function equal to 0. You follow me? Set your function equal to 0, and then you solve it. Well, if you set your function equal to 0, basically that's just where the numerator equals 0. The denominator equals 0 is undefined. So we really just say, okay, well, even if you want to think about it this way, multiply both sides by x cubed, you still get x squared minus 1 equals 0. What are my x-intercepts? Say what?
1 and negative 1.
1 and negative 1. Very good. You add 1, take square root, or factor. Either way, you're going to get x equals 1, negative 1. Are you okay with that so far? You sure? So numerator equals 0, no problem. That's how you find your x-intercepts for any rational function. Numerator equals 0. You got it? Now, y-intercept. Y-intercept says you plug in x equals 0 and you find out an answer. What do you get when you plug in x equals 0? -1 over, that's a problem. That means there is no y-intercept. And we're going to find out why in step number 2, but it does not exist. I'm going to erase little parts so we save space. But this is from x squared minus 1 equals 0. That gives us the 1 and -1. Step number 2, oh, step number 2 is a good one. Step number 2 is a good one. Step number 2 is where we find out all the asymptotes. Now, you might be thinking, who cares about asymptotes? Don't we have increasing, decreasing? The asymptotes tell you most of what you need to know for your graph. They really say, here's your sections. Here's what you're going to do in those sections. Basically, if you knew the asymptotes, you can almost guess what this graph is going to look like with just a couple numbers. So we're going to find our asymptotes, both vertical and horizontal. How do you find vertical asymptotes? No, not derivatives. We don't do calculus till step number 3, by the way.
Denominator equals 0?
Good. When the denominator equals 0, you're going to have discontinuities, right? Those discontinuities are either holes, if you can cross them out, or asymptotes if you can't. So you'd say x cubed equals 0, and x has to equal 0. Can you cross out the x cubed with anything? So then what that says is there's a discontinuity a vertical asymptote occurs where x cubed equals 0. Or in other words, x equals 0. That's going to give us a vertical asymptote at x equals 0. Now, listen carefully. If you were able to cross it out, you would do that. Okay, you'd cross out that discontinuity. You just keep in your mind that there's a hole there, all right? You'd have to identify the hole. So it's a little bit easier to asymptote. You'd cross out the problem. You'd say their hole exists at this point, and you put a hole on your graph. Does that make sense to you? That's what you would do. I think I've shown you how you do holes. I think I gave you x squared minus 4 over x plus 2. The hole would exist, actually minus 2. The hole would exist at, I did plus 2, at 2. And then you would find that value, you'd put a little circle there, and it would just be an undefined little point. You follow me on that? Okay, so that's what you would do with holes. Most of the time, I'm going to give you asymptotes. Most of the time. You will have some holes, most of the time asymptotes. How do you find horizontal?
Limit
Yeah, you're right. A limit as what?
as x approaches infinity.
So really, there's 2 of them, right? You got to check both. Don't just assume that it's going to be the same. A lot of times it is, but we've seen cases where you have different horizontal asymptotes. Hey, do you remember how to take limits of that stuff? I hope you do, because I think that's what your homework was on, right? Hope so. How do you take a limit as we approach positive infinity or negative infinity? Don't mumble it, say it.
Divide by the biggest, divide by the highest power of the denominator.
Very good. In the keyword, denominator, not numerator, denominator. So we would be dividing by x cubed, both here and here. If we did that, it's going to look identical to this. You'll get x squared over x cubed minus 1 over x cubed all over x cubed over x cubed. Can you see that this is going to go to 0?
Yeah.
Yes, no?
Yeah.
If you want the rest of it, here it is. I'm doing this one right here. You get 1 over x minus 1 over x cubed all over 1. True? Yes, no?
Yeah.
Okay. 1 over x cubed, 1. Tell me something, ladies and gentlemen. You need to know this. When x goes to infinity, what's this do?
0.
What's this do?
0.
What's this do? Stays at 1. That's 0 over 1. That's 0. Now, just think through it. Think through it. Is there going to be a difference if we go to negative infinity? This would still work, right? You still do that. You still have exactly this thing. You follow me? Now take it to negative infinity. What's 1 over negative infinity? We'd be over here right now. What's 1 over negative infinity? It's still 0. What's 1 over negative infinity? It's still 0. This would still be 0, and that's still a positive 1. Because you're dividing x cubed by x cubed. No matter what it is, that's going to be a positive number, positive 1. You follow me on that? You sure? Yes, no? I see some nods. They're like, Questions? Are you okay that this is equal to 0?
Yeah.
Okay. If it was going to negative infinity, so let me just change the problem here. Now let's say, aha. 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 Does anything change? Is it still 0? So, where are our horizontal asymptotes? 0. Both left and right? Both left and right. So horizontal asymptotes occur at y equals 0, both positive and negative infinity. Would you mind if I erased this? Do you need it? So I've taught you how to do the limits. You do the limits. Also, you're going to hate me for just telling you this, but you can see it just by looking at the limit. Where's the power bigger, top or bottom? That's something over infinity, right? That's going to be 0. Where's the power bigger, top or bottom? That's something over infinity, that's going to be 0.
However you want us, if...
I want you to show it. Yeah, I want you to show it. Yeah, but at least you can check your work really quick, right? So, this means as we're going to the right, we're going to 0. It's going to the left, we're going to 0. How many people feel okay with what we've done so far? Any calculus? Not really, just limits. Let's start doing our step number 3. What's step number 3? Let's do our first derivative test. Now, I know you all know how to take the first derivative, so I'm going to start doing these first derivatives a little bit quicker. Just stick with me on these derivatives. What you would do, take your quotient rule, and you're going to have this minus this. All over that squared. Still okay so far? Actually, I'll show the work if you really want me to. Low D high minus high D low, square the bottom, and we're okay to go. X cubed times 2x minus x squared minus 1 times 3x squared all over x to the 6th. Yes, no? Okay, so basic derivatives actually. What you do with them later kind of sucks, but basic derivatives so far. Y prime equals 2x to the 4th minus 3x to the 4th plus 3x squared over x to the 6th. So far, so good? Distribute, deal with those signs. You see where the plus is coming from, I hope. Y prime equals negative x to the 4th plus 3x squared all over x to the 6th. Can you keep going? Can you factor, simplify? Yes, factor out an x squared. That is going to make your work later easier. Would you agree that that is your first derivative? Ladies and gentlemen, are you okay on your first derivative? I've gone kind of quickly through that, but I'm assuming that at this point you can do a quotient rule and simplify it. You follow me? Nudge your head if you feel okay with it so far. Yeah. What is this? I know it's the first derivative. What is it?
Increasing or decreasing.
It's going to give us increasing, decreasing because this is it's a slope. And if slope is positive, you're increasing. If slope is negative, you're decreasing. If slope is 0, you have a potential relative max or min. You follow me? So what we're going to do for the first derivative test is you go, okay, now I want to set this equal to 0. And what we're going to do on this is pick out all the points that are undefined and all the points that have a 0. So can you please tell me for my critical numbers, that's what we're talking about here, for critical numbers. The first one I see is x equals 0. Where am I getting x equals 0, ladies and gentlemen? That tells you that, right? That says x equals 0 is an undefined point for your slope. That could mean that you're changing between increasing and decreasing. Does it have to? No, but it could. It could mean that. Do you follow that? So you have to have the x equals 0. Make sure you have where the denominator equals 0 on your critical numbers and for your inflection points later. You've got to have that. Secondly, you're going to set the numerator equal to 0. That's the same idea as over there. It's very much like finding roots. Numerator equals 0 is going to give you the actual numbers that makes your slope equal to 0. You follow me on that one? Okay, so if you want to multiply by x to the 4th, you would see the same thing, wouldn't you? Wouldn't you? Okay. How do you solve that?
Subtract 3 over.
I would probably add x squared and then divide and then take a square root. And you could subtract 3, divide by -1, take a square root. It's just more work. But you're going to get, somehow, you're going to get x squared equals 3. True? Well, that means that more critical numbers occur at plus or minus square root of 3. So I have x equals 0, x equals root 3, which is why I had you take your calculators out, because I can't do that, and negative root 3. Those are my critical numbers. You okay with your critical numbers? Yes, no? Take a square root of 3. You have 3 and root 3. 1.7 something. What's next? Now, the reason why we simplified this as much as possible is for our second derivative. Let's go ahead. I'm going to do the second derivative. Why don't you try on your paper as well. See if we can match up with the right answer. So step number 4 is our second derivative. Okay. Oh, that's not as bad as you thought, huh? Hopefully not as bad as you thought. Did you get that far? If you're still going, still go. That's fine. Distribute, combine like terms, factor, simplify, you're going to get down to that point. Let's all make it down to this point. Are you okay that that is your second derivative? You know how to do the second derivative already. That's not the issue with this problem, okay? I know you know how to do that. Your point now is, let's find our possible inflection points, or the numbers where we are going to change concavity. Can you tell me from here the numbers where I'm going to change concavity? I'll tell you one of them. So possible inflection points. I'll tell you one of them. One of them is x equals 0. How am I getting x equals 0? Yeah. In fact, you know what? That's kind of a key point for us. That was an undefined point from the very beginning, right? If you take a quotient rule, look at that. It's going to come back again because you're just squaring it. Take a second quotient rule, it's going to come back again because you're just squaring it. So that's going to be undefined. It's going to be a critical number. It's also going to be a possible inflection point where we change concavity. It shows up a lot in our problem. You okay with x equals 0? Now, the factoring is nice for us because it says if you set this equal to 0, which is what you're supposed to do, you can clear out the denominator. We had to include that point because it did make an undefined second derivative, so we do have to include it, the x equals 0. But now you can say, 2 times x squared minus 6 equals 0. You set the numerator equal to 0. Are you with me on that one? Yes, no?
Yes.
Okay, but the 2, does the 2 do anything for you? So if you divide by 2, basically you're going to get x squared minus 6 equals 0. You're going to get x squared equals 6. And you're going to get
Plus square root of 6.
okay, yeah, I understand. Not very nice numbers, I get it. But, can you find them?
Yeah.
Now, the point is, as soon as we do our first and our second derivative, we're going to make our table up. From our first derivative, it said you're going to have something special happen at 0 maybe. You're also going to have something special happen at the square root of 3 and the negative square root of 3. Are you okay with the points that we got from the first derivative, everybody? Are you all right with that? Negative root 3, 0, 0 especially, and the root 3. Are you okay with that one? Now the next one says, okay, you still have from our possible inflection points, 0. Then you have root 6 to the left or to the right of root 3. It's actually pretty important to put this in the proper order, right? So you have to have root 6 over here somewhere. And negative root 6. Now we're going to do what with this? After you find those numbers, are they hard to find? Not really. Not really. What do you do now? After you have the negative root 3, 0, root 3, what do you do?
Plug them into the derivatives.
Wait, plug that in?
Yeah.
That's going to give you 0.
Test them in the
Test.
original function.
If I plug that into the original function, that will give me points, which I'm going to have to do in step number 6.
Numbers between intervals.
Oh, test, yeah, test
Yes.
each interval.
Look, you need to know what happens here. You need to know what happens here, 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 here. All those little intervals, right? You've got to know which area to plug them into. Where am I going to plug in points from all these 4?
First derivative.
That's why we have that first derivative. And these are going to go into the second derivative. So let's go ahead and try that. For this one, I'd plug in negative 2. I'd plug in negative 1, 1, and positive 2. We do it in the first derivative. So if I plug in negative 2 here, so f prime of negative 2, f prime of negative 1, f prime of 1, f prime of probably positive 2. I don't really care about the actual value, all right? I really don't. I care about the sign, positive or negative. So we're going to take negative 2, plug it into the easiest one to work with. That's this one. If I take negative 2, I know I'm going to have negative 4 plus 3. That's a negative number over a positive number. Did you get a negative as well?
Yes.
negative. Hey, what's negative mean in relation to this? Decreasing, very good. Because it's a slope, negative slope means decreasing. Plug in negative 1. If I do negative 1, I get, remember that you don't square this negative, right? That says negative x squared. So this will be negative 1 plus 3, that's 2, over, it's positive. What's positive mean? Increasing. Don't just say up, because that could be misconstrued as concave up. I want to say increasing or decreasing. How about 1? Let's try 1. If I try 1, do you see I'm going to get the same exact thing as negative 1? Because that says negative 1 plus 3, that's positive over, that's positive. So, is that a relative extreme? This one. No, that 0 actually didn't change, right? We're increasing and increasing again. That's interesting. How about that, the 2? Negative. It's going to be negative, yeah, for sure. You plug in the 2, you get negative over positive, that's a negative. Now let's try our second derivative. If we do, for those of you who really have the hang of this, can you do me a favor right now? Can you start finding me points? I think I can pretty much take care of the 0, but I'm going to have a hard time plugging in the square root of negative 3, root 3, negative root 6, and root 6. So if you want to try this as I'm going through the second part, if you really get to grasp this. Left side of the room, my left side, you guys try the root 3 and root 3. You guys try the negative root 6 and root 6 in the original. Okay, can you do that for me? Give me to like the first, I don't even care, the first decimal place is fine, 2.5 or whatever. Now, for our second derivative, we're also going to try some values in these intervals, but you're going to plug them into the second derivative. So f double prime of, that's going to be like negative 3. Double prime of negative 1. Double prime of 1. Double prime positive 3. If I do that, if I take the negative 3 over here, that's going to be a positive over a negative. I have a negative. What's negative mean, by the way, when I'm talking about second derivative? Concave down. If I plug in negative 1, notice what we do. We've got 1 minus 6, that's negative 5, over negative, that's going to be that's a positive. Concave up. If I try positive 1 here, I'm going to get a negative over a positive, that's going to give me a negative. And if I try 3, I have a positive over a positive, that's going to give me a positive. By a show of hands, how many people feel okay with our concavity at this point? Right, are you guys okay with this? You guys over here, yes, no? So we've checked this in the second derivative. We got, this was a negative interval, positive interval, negative interval, positive interval, concave down, up, down, up. Were these inflection values? Does concavity change here? And here, and all of them. Actually, we had different concavities. Step number 6 is you have to find all of your points. So right down here, I'm going to write my points. I know for my x-intercepts, I'm going to be at 1, 0, and negative 1, 0. My y-intercept, I didn't have any, so that just came from my x-intercepts. Now, I also have all this junk over here. So my relative max and relative min, can you tell me which one of these is going to give me my relative maximum? My relative maximum, is it going to be the negative root 3 or the positive root 3? Positive. This one's going to be a relative minimum. So relative max relative min. The relative max will be at square root of 3 comma something I don't know what it is. Negative square root of 3 comma something. Somebody plugged in the square root of 3. About how much did you get? 0.38?
Yeah.
Okay, so let's say 0.4. Is that negative 0.4?
-0.38.
Okay. Are you okay getting those numbers? Do you remember where I'm getting these numbers from? Where do I plug in the root 3's? Not the first derivative, not the second, but the original function is going to give you points. Are you okay on that so far? You sure? We're almost done. Almost done. Now, let's do the root 6's. The root 6's are my inflection points. Negative square root of 6. And the square root of 6. Somebody plugged in the negative square root of 6. How much do you get? Now, this is everything that you need in this little block to graph this. So I'm going to erase this because we don't need it anymore. Get everything. Well, almost everything. I'm going to leave the asymptotes because I need those. That's going to be important. You're going to kind of see what I want from you on this. The first thing that you should do, put out your asymptotes, wherever those things are. So my asymptotes are at x equals 0, x equals 0 horizontally, both right and left, and, I'm sorry, y equals 0, both right and left, and x equals 0 for our vertical. So we know we have some asymptotes. Next thing you do, put down your points. Your x-intercept is at 1, 0, and negative 1, 0. Your y-intercept, you don't have one because you have an asymptote there. You don't have that. Your relative max and relative min. Square root of 3 the square root of 3 is about 1.7, somewhere around there. So the relative max occurs at... Okay, so there's a slight error in class. The numbers that some of the students gave were a little bit off. Here's the correct numbers. Now, we went through this a couple times, so of course if you watch the video, you're like, whoa, what's going on here? Why are these numbers changing? Here's where the number's changing. When you take the root 3 and you plug it into the original equation, which gives you points, what you actually end up getting is 0.38. If you take negative square root of 3, plug it into that original equation, you're going to get negative 0.38. Now, when you take the square root of 6, you plug it into the original function, what you're going to get is 0.34 and negative 0.34. They're very close points. Now the graph's going to look somewhat similar, but you'll notice that on the video I have that as 1 and negative 1. If you just change that to 0.5 and negative 0.5 and just extend that graph even further, this is about what it looks like. The picture of the graph on the video is just fine. So here's what you would end up doing. You would still have your same x-intercepts. You would have your relative max and your relative min. You would have your inflection points. They're just really close together. So our graph, as you can see, we're still decreasing. That's what this means right here. Decreasing concave down. So we're dropping and we're concave down. That's this way. Also, we have this horizontal asymptote. That's what that was so important for, was to tell us that our function is not going to be going way up like this, not going to go way down like this. It's going to be riding along this x-axis. So it must look about like that. Not exactly like that, but pretty close to that. Then from this point to this point, that's this little interval. It says you're still decreasing, but you're concave up. Your slope is starting to increase. Your function's still decreasing, but your slope is getting more and more, it's getting larger and larger. So we're going to decrease concave up, and then right after that point, right here, it says you're still concave up, but now you're starting to increase. And what that does is increases all the way up until you get to 0. Now, at x equals 0, you have a vertical asymptote, which means that you're never going to reach this y-axis. All that's going to happen is if you're still increasing, as you get closer and closer, you're going to shoot up to positive infinity. So that's what the horizontal asymptote said. It says you are increasing. You can't be decreasing. You're increasing all the way up until x equals 0. That says horizontal asymptote. And you're concave up the whole way. Now the other picture is, it's going to look very similar to this, only kind of rotated a little bit. Starting from 0, you're increasing and you're concave down. That's this way, increasing concave down. Now because again you have this vertical asymptote, the only way you can be increasing and concave down and have this vertical asymptote is by shooting up just like this. You can't come down, that would be decreasing. So you're coming up like that. Coming up just like that. Now we reach this point, that is our relative maximum. It says at your relative max you switch from increasing to decreasing, but you're still concave down for that whole interval. So increasing to decreasing, but concave down. That's that little point right there. After that point it says you're decreasing for the rest of your graph. You're decreasing the whole way, but now you're concave up. The only way we can decrease the rest of the way and be concave up and associate this horizontal asymptote is by putting it right along the x-axis, just riding that thing all the way out. And that's the same picture that you have on your graph. That's an inflection point. Now, how in the world does this graph look? That's why I have the table. This is pretty interesting because we're going to associate all this stuff with our asymptotes. Now, check it out. You know that this has to go close to this one, this has to go close to this one, has to go here somewhere and there somewhere, right? Now, here's what it says. It says you're going to be decreasing. Decreasing is like this, and you're going to be concave down. That's this way. Does that make sense? All the way until you get to this point, that -√6. That looks like this. Decreasing, concave down. Do you follow me? That's the only way you can have it. If you're decreasing concave down up here, you fail the asymptote. You have to be with the asymptote. That's why asymptotes are important. It says you're going to be at that asymptote right there. You see what I'm talking about? Okay. From here to here, this little interval says you're decreasing, but you're concave up. So this part, decreasing down. This little part, decreasing up. That's the inflection point coming back at us. That's this. That's concave up. You see the decreasing concave up? Then this part says increasing concave up. That's this way. And you actually do that all the way to 0. Now, how do we go all the way to 0? Where do you think this is going? If it's increasing and there's an asymptote, does it magically go back down here? Otherwise, we have another relative max, wouldn't we? It's going to go all the way to infinity. There's an asymptote, folks, an asymptote. It has to go to the asymptote. So if it says increasing, concave up to 0, it's going like this. Forever. Is there any other way that it could be and still have the asymptote? Nope. Now the rest of it, the other side of the graph. The other side of the graph says for this interval up to √3, you're increasing, you're concave down. That's this way. You follow? Increasing concave, but you also have an asymptote, so you have to meet the asymptote. Increasing, concave down. That's increasing concave down until you reach a relative max. You know that's a relative max. Then it says for this little interval, you're decreasing and you're concave down. Decreasing and concave down. That's this way. So for here, you're going to go, down. And then from here on out, after that √6, remember that's our √6, you're going to be decreasing, but you're concave up. That's this way. And you have to meet that asymptote. That's there. As good as we can do. But that's a pretty darn good graph for just having for no graphic calculator. That's pretty good. How many people were able to follow that? Now, you gotta be careful. Be careful with these numbers. You messed me up, but that's okay. Be careful with your numbers of your own. Now, we only got through one example. If you want to hang out just a little bit, I'm going to try to do one more. All right, we're going to do one more example. How to graph some rational functions. I'm going to try to go all the way through it, but I'm going to be erasing things as we go. So it might help you to write this down as we're going through it. That way, when I erase it, you're not like totally lost. So I'm going to save some space. I only have a limited board to work with. So let's start with our x and y intercepts. That's always step number one. X-intercept says, where is the numerator equal to 0? That's the only places where this function can actually equal 0. If the denominator equals 0, then we're undefined. We have either wholes or asymptotes. So in our case, x-intercepts are add 8, divide by 2, take a square root, plus and minus 2. I would write that a little bit lower. Okay, y-intercepts. You plug in x equals 0. What you have is 0 minus 8, 0 minus 16. Negative 8 over negative 16 is positive 1/2. Vertical asymptotes, those occur where your denominator equals 0 and you can't cross it out, you can't simplify. If you were able to simplify it, it would be a whole. But if you're not able to simplify it, that's a vertical asymptote. So when we have this denominator equal to 0, again, well, it's different squares. You can factor it, you can add 16, take a square root. Either way, you're going to get x equals 4 and negative 4. Now, x plus 4 and x minus 4, they do not simplify with our numerator. That means they're not wholes. They are, in fact, asymptotes. All right. Now, as far as our horizontal asymptotes go, that says what happens when we take x to infinity and negative infinity. And that's dealt with a limit. If you notice that we have our leading terms, polynomial here, the powers are the same. So when you do that whole divide by the largest power in the denominator thing, you're going to divide by x squared. What that's going to give you is 2, 0, 1, 0. So basically you have 2 over 1. That's going to be 2. Also notice that it doesn't matter if I have negative infinity either. You get the same exact thing. What that means is we have a horizontal asymptote at 2 to the right and 2 to the left. So I'm going to erase this now. We know our horizontal asymptotes are at 2 either way. Y equals 2. Now, as far as our first derivative test and second derivative test, here goes our derivatives. Try to follow along. Again, I'm going to erase this when I'm done. That's our first derivative. Now what the first derivative says is slope. Where slope is positive, you're increasing. Where slope is negative, you're decreasing. Where slope is 0, you have the potential for a relative max, relative min. Or something interesting could change, maybe around an asymptote or something, change from increasing to decreasing. We've seen that before. So the ideas are, find all the places where the numerator and the denominator equals 0. So in our case, the numerator equals 0 when when negative 48x is equal to 0. That says x equals 0. That's going to be one critical number. That possibly is a relative max or relative min. Now, where the slope is undefined, it's not necessarily a critical point, but it could change from whether the graph is increasing to decreasing or vice versa. So, in our case here, hopefully you can see this. Denominator equals 0 when x is 4 and negative 4. It's not coincidental that that's our vertical asymptotes. Those points can come up again, especially with the quotient rule, when you notice you're just squaring the denominator. So 3 critical values that we're going to be putting on our first derivative table. We've got our 0, our 4, and a negative 4. Take a look at this. Hopefully you've written this down. I'm going to erase this right now and write it right up here. That way I can work on my second derivative. And what we got out of that again was 0, 4, negative 4. Okay, second derivative test was going to give you concavity. So let's take the second derivative, see what we get. Again, write this down, erase it when I'm done. This is going to be to the 4th power since we're squaring that square. Notice the plus, I'll change that right now, just make a negative into a plus. Also, I'm going to take a shortcut here. I know I tell you not to do this, but we're going to take a general power rule times the derivative of the inside, and that should be our derivative. Now we're going to do a little fancy math here. We're going to simplify a couple pieces, but I'm going to leave a couple pieces alone because I want to factor it. I want you to see the factorization. So hopefully you see what I've done. I've multiplied the 2x times the 2 and this x to make it 4x squared. I've leaving the 48 alone because I want you to see that factorization. It just makes things a little bit easier for us. So I'll be factoring out my 48 from right here. Also I'll be factoring out x squared minus 16 from here and one of them from right here. So what that's going to leave us with, be careful on your signs. Check this out. Factor out your 48. Factor out one of your x squared minus 16s. What you're left with is negative x squared minus 16. Negative, and one of those is remaining. Plus the 48 is gone. We have 4x squared. The x squared minus 16 is gone. Check it with distribution if you really want to, but if you distribute this in, that's negative 48x squared minus 16 squared, plus 48 times 4x squared, and then x squared minus 16. So that's the correct factorization. Almost done. One last little step. What we're going to do is simplify this a little bit. If you look at that, that's negative x squared plus 16 plus 4x squared. That's 3x squared plus 16. Also, we're going to simplify out one factor of x squared minus 16. So gone, part of that's gone. That's our second derivative. That's about as good as we can make it. Now, what the second derivative is, again, it's concavity. It's how your slope is changing, or in other words, the curvature of your line, of your graph, if you will. So whether it's increasing or decreasing, we can have two different types of that. We can have increasing concave up, increasing concave down. We can have decreasing concave up. We can have decreasing concave down. Just like that. So what this says is to find those points where you change, where you possibly could change concavity, set your numerator equal to 0 and your denominator equal to 0. The numerator gives you the possible inflection points, like the actual numbers, the values, where you can plug them into the actual function and get a point. The denominator says where the second derivative is undefined. Well, it could still change concavity at those places, but you probably won't find a point because it's most likely an asymptote. So here, if you try this, well, notice that. 3x squared plus 16. Is that ever going to work for you? 3x squared plus 16 equals 0. Well, 3x squared equals negative 16. X squared equals negative 16 over 3. Can you have x squared equals negative? The answer is no, not in the real number system. So here that's not going to give us any possible inflection points. So the numerator pretty much doesn't give us anything. The denominator, you're going to see again, those same points keep popping up. Even from the beginning of our function, we had 4 and negative 4 as being undefined. That happens here as well. So again, we're going to have the points 4 and negative 4. Okay, again, take a close look. That's our second derivative, all worked out for you, nice and pretty. Set equal to 0, numerator, nothing. Denominator, same points we've gotten before. I'm going to erase it, and then we're going to talk about step number 5. We'll plug all this stuff in, we'll make a nice table, we'll have the points from our original function in step number 6, and then I'll graph it. And what this gave us was 4 and negative 4 again. Now when we make the table, hopefully you remember this from class or from previous videos if you're watching this on video. We put our first derivative up top, second derivative on the bottom, and basically it gives us a kind of a concise version of our graph, of our function on a graph. So we're going to put all of these points on the top, got to be in order. And these points on the bottom. And what we do is we test specific points in each interval, and what that's going to tell us is where our graph is increasing or decreasing for the top, that's our first derivative, or concavity for our second derivative. So I would test the points like -5, -1, 1, and 5. And we're testing them in the respective derivatives. So here, we'll be using the first derivative. On the bottom, we're taking second derivative, so concavity, and we'll test some similar points, but make sure you put them in the second derivative, not the first, not the original. Original function gives you points on a graph. First derivative gives you increasing or decreasing, second derivative gives you concavity. So let's try this. If you want to try it at home, plug in your own points. But we're going to try f prime of -5. That's a negative times a negative. This is our first derivative. Again, remember, first derivative. Negative times a negative is a positive. That's a positive because it's squared. That means that this is positive. You don't exactly care about the whole value of it. You care whether it's positive or negative. Increasing. -1. Well, that says negative times negative is a positive over a positive. Again, that is positive. Increasing. Next up, we have 1. Negative times a positive is a negative over a positive. That's going to be a negative. Decreasing. 5. Negative times a positive is a negative over a positive is still a negative. Decreasing. Second derivative is telling us some more things. It'll say plug in -5, but now do it to the second derivative. Second derivative is right here. This is, well, let's see. -5 squared, well, that's going to be positive, plus positive, positive, oh, that's positive. Oh, you know what? I made a mistake. I think I drew that wrong. If you were watching at home, you might have noticed it. What's Mr. Leonard thinking? That should be a power 3. I was kind of thinking through that, thinking, wait a second, that doesn't make too much sense. So let me change it to a positive 3, and then we're gonna check this point again. I think that one's gonna work out for us. But make sure you have a 3 right there, because that would be a big mistake. I forgot to. I erased it before I copied it down, so bad mistake on my part. Let's check it one more time. Let's check the -5. So -5 squared, that's positive, times a 3 is positive, plus 16, still positive, times 48, that's positive. Now let's check it down here. We have -5 squared, that's 25. Minus 16, well, that's still positive, and when you cube it, it'll still be positive. So we're okay on the concave up. It's still going to be concave up. This is the one that's going to be changing for us. If we plug in 0, well, that's 16, times a positive number, that's still positive, but look what happens down here. 0 squared is 0. Minus 16, well, that's a negative. What happens when you cube a negative? Well, it's still a negative. So this is going to be concave down. And it's concave down for its entirety. Notice how we didn't get that 0 in our second derivative, so that's not going to be a place where we're changing concavity. 5, same thing's going to happen as -5. We're going to have a positive up here, we're going to have a positive down there. That's concave up. Well, that takes care of step number 5 for us. So far we've found our x-intercepts, our y-intercepts. We've gone ahead and done our first derivative and our second derivative. We made up our table. We have all of our intervals of increasing, we have decreasing, we've got concavity up there. We're almost done. What we need to do right now is find out some points, what our points are, plot them on our graph, and look at how this is going to be graphed for us. So, points. Well, our points are already on the board. We have our x-intercepts, we have our y-intercepts, and we have our asymptotes. You're going to notice that all those points come back again at us. We have 0. Well, if we plug in 0, you get 1/2. That was our y-intercept. So all of our points are basically listed. We've got 2, 0, negative 2, 0. Those are our x-intercepts. We've got 0, 1/2. Keep in mind what that is though. That's our y-intercept, and it's also, if you look at it, it's also this, which is increasing to decreasing, increasing to decreasing. That's a relative max. Relative max. Is there a relative min? No. This says increasing, increasing, decreasing, decreasing. There's no way we're having a relative min here. Doesn't happen. Also, inflection points. We could try for inflection points. We could try for some of these points, but you'll see when you plug them into your original function, you've got 4 squared minus 16. You've got negative 4 squared minus 16. That's undefined. That's how we got those asymptotes in the first place. So these things are all asymptotes. What it means is we only have 3 points to graph. Now, I told you in class or on the video that a lot of times you can actually graph these graphs just by looking at the asymptotes and increasing and decreasing. I'm going to try to show you that right here so that you can kind of visualize what it's going to be even without the second derivative sometimes. So if that's what you're looking for, this is the part that you want. So, number 1, do your asymptotes. Asymptotes are vertical, 4, negative 4. Hopefully you're okay with our asymptotes. Horizontal says 2 in each direction. Now, keep in mind, horizontal asymptotes only work as you're going to infinities. So, could you cross it here? You could. It doesn't mean it's like a wall for you. Well, it's a wall for the y. Yeah, for our vertical. But horizontal, not necessarily. So horizontal says 2 in both directions. But it only starts out here. The next thing you do after you take care of your asymptotes in your graph, you're going to plot all of your intercepts. So our intercept says 2, 0, negative 2, 0, and 0, 1/2. We're going to label what they are too. I've showed you that when you label these points, well, they're intercepts, those don't do much for us besides say you cross the x-axis here. But that said, you have to be a relative max. That's what that said. We listed it as. Now just think about it. Even if you don't have the second derivative, so let's just pretend I didn't even do the second derivative. What's the only way we could fit this information on this graph with just the first derivative? So hint, hint on that test. If you're looking at how do I do the graph with just the first derivative, sometimes you can do it. This is one of those cases. Sometimes you can't. You need the second derivative. But a lot of times, if you have asymptotes and you have increasing, decreasing, you can picture what this graph looks like. Here's what I'm expecting from you. If you know that your asymptote goes this way and this way, there's only 2 scenarios. You're either going, and you don't have any relative max or min. Notice you don't have any of those in this interval. You don't have any of those in this interval. You do have one in this interval. But other than that, there's no change in increasing. There's no change in decreasing. So unlike the previous example, we can't do things like this. Otherwise we'd have a relative max. We can't do things like this. Otherwise we'd have a relative min. It's either going to be up or down. That's it. It's the only thing we can have. So when you look at it, if there's no relative maxes or mins, there's no change in increasing, decreasing, look at the first 2 intervals. It says you are increasing all the way to 0. You're increasing all the way. So from, actually to negative 4, that's where we're really looking. From negative infinity to negative 4, you're increasing. Can this be increasing? No, that would be decreasing. Increasing says this way. So to fit this on a graph, if you have a horizontal asymptote and a vertical asymptote, that's the only way it can be. That's it. Now, what about this section? This section says you're increasing from -4 to 0, you're increasing from -4 to 0, and then you're decreasing from 0 to 4. Well, what's the only way that you can increase and then decrease and have one relative maximum and touch these 2 points? The only way it could possibly look is going up and coming down. That's it. I'll talk about concavity in a minute. Just want you to see the idea of fitting your graph to asymptotes first. Now, after +4, it says you're decreasing. Decreasing, mind you. Like this? No, that would be increasing. Like this? Yes, that is decreasing. There's no relative max, no relative min. That means you're decreasing throughout. It means you have to go from left to right, downward. The only way you're going to fit this asymptote and this asymptote is with a picture like that. Now, I have gone ahead and done the second derivative for you, and I gave you the table as well. If you want to go that far, that's fine. In fact, most times you really should. I'm just trying to get you to think outside the box here. But if you compare the concavity with this, let's see if it works. It says you're increasing and you're concave up, all the way from -infinity to -4. Increasing and concave up looks like this. Ah, that's what we have. Increasing concave up. Then on this interval, from -4 to 0, that's here, it says you're increasing, but you're concave down. Well, look at that. If you have these asymptotes, increasing concave down, that's exactly what we did, and we fit it to our points, -2, 0, and 0, 1/2. We had to do that. From 0 to 4, you're decreasing and you're concave down. Decreasing concave down looks like this. So from here, we're decreasing 0 to 4 and concave down. Hey, that works. Last section. From 4 onwards, we're decreasing and we're concave up. Decreasing concave up looks like that. Decreasing, concave, we got it. That's our graph. Do all 7 steps, you have your picture. But sometimes with these rational functions, if you have those asymptotes handy, you can sometimes take your first derivative and just look at that graph and put it in the right places. And the concavity does work out for you.